Welcome everybody on YouTube. So we just went through an example of adding exponents. I forgot to hit the record button, but we're recording now. And we're gonna go through another example where we're going to see what happens when we divide. Okay, so we have an exponent rule that looks something like this. Anytime I'm dividing two things with the same base, what we're gonna do is we're gonna subtract our exponents, right? So I'll leave that up there. That's our general rule. And so on the similar theme, we would have something like this: 2 to the 5th divided by 2 to the 4th. And we want to figure out, hey, well, what would this mean in our context here? So in the numerator, right, what I have up here, right, so what I have up here in red, this tells me that the 5, I have 5 copies of 2s, right? So the numerator is going to look something like this. And then in my denominator, the 4 means I have 4 copies of 2s. So I have 2 times 2 times 2 times 2. Okay? And so when we say we're subtracting them, we're going to have some sort of cancellation that happens, right? So we'll be able to go through and sort of cancel our 2s. And I have 5 copies on top. And effectively what I've done is I've gotten rid of 4 copies. And so what this ends up being is, ultimately there's only going to be 1 2 left over. But where that came from was we had a 5, and then we took away 4 of them in the denominator. And then it ends up being just 2, or if we wanted to, we could write this as 2 to the 1st power. Okay, so another example here where what we're doing is whenever we're dividing, we have the same base. So it's really important that this 2 and this 2 are the same. Like these A's, this is the same letter that we're using here. So it's really important that those 2's are the same. Okay, so this is our second exponent rule. We're going to subtract exponents. So far, so good. And then, so if we keep going here, right? So if we keep going, so I'm going to add a new slide just to be quick here. We could also think about this rule, right? So if I have an exponent to an exponent, so to match our notation here, I'm going to use a to the m raised to the nth power. Okay. So now we're getting a little bit more complicated. So we would look at something like this. We'd have a base of 2. We're going to use that again. And say I have 2 to the 4th raised to the 3rd power. All right, so we're going to think about, our rule tells us that what we should do is really this should be a to the m times n, right? So we should multiply m and n together. And we're going to see sort of why is that? Why would we do that? And it all comes back to the idea that what this means is we have 3 copies of this, whatever's inside our parentheses here. Okay, so we're going to have 3 copies of 2 to the 4th. So we'd have 2 to the 4th times 2 to the 4th times 2 to the 4th, right? So we're going to, that 3, so we'll go ahead and highlight this in red. This 3, what it means is we have, right, 3 copies of 2 to the 4th power. So if we go back, we said with our multiplication, what we're going to do is we're going to add, right? So we're going to add our exponents together again. Okay, so we're going to add them, and we say that this is same base. We're multiplying our bases, so this would be 4 plus 4 plus 4, right? So that was back from the first rule that we used. And so we can see here that we have 3 copies of 4 in our exponent. And so this is going to be 2 to the 4 times 3, right? Or in other words, this would be 2 to the 12. Okay, so when we think about this, in order, what we don't have to do, right? So we can use these rules. So the rule that we're showcasing up here is this one, right? So I'll go ahead and highlight this in yellow, right? So this is the rule that we're highlighting. And what it allows us to do is, instead of having all of this stuff in the middle, right? So instead of going through all of this every time, there's a lot of work there. Us understanding the rule says, hey, I can go just right from this expression straight to this one down here. Okay, so the rule allows us just to bypass all this and say, hey, I'm just going to go straight down here, and I know what this should be 2 to the 12th. Right, and so this stuff in the middle, what we're doing is we're highlighting, hey, why, right? Why does all of this work? Okay, so these are sort of our basic ones, right? So our basic exponent rules. When do we add? When do we subtract? When do we multiply? And if we, so do you all still have access? Did you bring up the document on Plato? Are you looking at the exponent rule document right now? So Carrie is, yeah. Jody is. All right, so down at the bottom, we have definitions of negative and fractional powers. Okay, so some of the other things that we are going to see that are particularly important are anything to the 0 power. So you may remember this one, right? So if we have any non-zero number raised to the 0th power, we're going to call that 1, right? So what this means is, hey, if I have, say, 5 to the 0th power, that's going to be equal to 1. And so any number, as long as it's not 0 to the 0th power, then we're going to make that 1. Some things that are also very important, whenever you have a negative exponent, a to the negative n like this, we're always going to think about that as being in the denominator. Okay, so 1 over a to the n. So again, this is another rule. So very important, whenever we see this a to the negative n, will be 1 over a to the n. So a quick example of that. So if you have something like, 5 squared divided by 5 cubed, if you used your subtraction rules here, it would tell you that this should be really 5 to the 2 minus 3, which is equal to 5 to the negative 1. Okay, so if I have 5 to the negative 1 power, without this rule right here, I really don't have a great interpretation of what 5 to the negative 1 is. But what we see is, hey, really what I should be doing is this should be, right? So this should be the same as, so I'm going to do this in blue here. Well, I would really have 5 times 5 over 5 times 5 times 5. And if I make some of these cancellations, right? So if I make some of these cancellations, really what I'm left with is 1 over, and there should be a 5 in the denominator. Okay, so these two things right here, really these should be the same, right? We really want those things to be the same. Right, so 5 to the negative 1 and 1 over 5. And then the general property is this one over here. And sort of the last, sort of the most important thing from this list, so these two are particularly important. And then what if we have a fraction? Okay, so if I have a to a fractional power, like 1 over n, something like this, then we can view this as a root, okay? So this is the most general form. But if we go ahead and think about this, why do these group? Okay. All right, so I'm going to go ahead and bring this onto another slide so we can view this. Okay. So a to the 1 over n is we're going to take a root. So the most common one that you're probably going to see is a to the 1/2, and that's the same as the square root of a. Okay, and then if you do a to the 1/3, that's going to be the same as, we would put a little 3 here, and this would be the cube root of a. Okay, so a to the 1/2, that gives you your square root. Okay, so the square root of a as an exponent is always going to be 1/2, and then a to the 1/3. This will be the cube root. And so more in general, any number you put down there, so you could have a 4th root, a 5th root. These are probably the one that you see most commonly, especially in calculus. So my calculus students are particularly using this one a lot, right? So it's very helpful for us to think about square roots being to the 1/2 power. Okay. All right, so let's take a minute here, and I want to kick it over to you all and give you a chance to work on some of these. Now, we only have 4, right? So there's only 4 of us here, so I'm not going to put us in breakout rooms. But if you look at the exponent rule practice, let's see if we can work through, say, I don't know, maybe the first 10 of these, right? So 1 through 10. So I'll bring that up, and we'll go ahead and pause for a minute here so you can all do some work. How does that sound to everybody?
I have a question.
Mm-hmm.
So what if you have a negative fraction?
You have a negative fraction. Okay, so you want to give me an example, like negative
So
1/2?
one, yeah, sure. Like negative fractional power, though.
You have a negative, a fractional power. Okay, so
So
let's,
like n to the negative 1/2.
okay. So let's make it a number, right? So let's say 5 to the negative 1/2, okay? What do you do?
Mm-hmm.
Okay, so so as I would interpret this, I would look at this first, and I would look at the negative sign, and then I would interpret the 1/2, right? So I would break this up into 2 things. So the first thing that's going to happen is the negative. Oops. The negative is going to make this 1/5 to the 1/2 power, like this. And then we could turn the 1/2 into the square root, so we could rewrite it like this. Okay. And so any of these forms are equivalent, right? So depending on how you want to represent it, how you want to write it, you could write any of these. So you could write it like this, as this, or this. They're really all saying the same thing. And so if you want to think about this in different ways, you can. If you plug any of these, say, into a calculator, and if you plug them into Desmos, they would all give you the same answer. So it's just 3 different ways of representing the same thing.
Okay.
Okay, so what we're going to see is we're actually going to try to figure out what the equation are for exponential functions, and we're going to need these rules here. Okay. So I guess to partition this a little bit better, why don't you all try the first 3, right? So try 1, 2, 3, and then we'll come back. We'll talk about those, and then we can keep going and do, say, 4, 5, 6. All right. So are you all trying these right now, or do you need more time? We'll look at number 2. Yeah, we can look at those. Okay. So Nick, are you working on them? I know that you've been chatting.
Yeah, I just started.
Okay. So Carrie, yeah, we'll look at number 2 in particular, but we'll give everybody a minute to catch up to you. Okay, so let me go ahead and I'm gonna clear all this out. And while you're thinking about them, I'll write them up here for this. So did we get through these three?
Yep.
We're good. Okay. So so what do we get for this first one? So what did you all get for number one? 3 to the 9? Yeah. Yeah, so we got 3 to the 9. Yep, so when you look at this right here, you're just gonna add these, you're gonna add these up. So you take 5 plus 8, that's 13, minus 4 is gonna give you 9. Right, so you went through, and this was our rule for adding exponents, right? So we went through, we added, right, added our 3 exponents here. Now, these next two are particularly tricky because one of them is going to give you a negative number answer, and one of them is going to give you a positive number answer. And so when you look at this right here, so see how you have this negative sign, the two things that I want to point out to you, there's a difference between these two negative signs, right? One of them is in parentheses, and one of them isn't. Right, so one of them is not in parentheses. So in our mathematical notation, when we look at this form right here, this is telling us that this negative does not go with the 4. Okay, so this does not go with our exponent. And then if it is in, right, so in the parentheses, we would say this goes with the exponent. Okay, so the question is, what do we have 4 copies of here? It's when I look at this, we have 4 copies of something, and the thing that we have 4 copies of is 3. Okay, and down over here, we have 4 copies of -2 that are appearing in our denominator. Okay, so these are distinctly different. So what we would have here is we'd have negative, and then we'd have 4 copies of 3. And so if I wanted a number for this, I could multiply these out, and I should get -81 here. Right? So this would be, the interpretation of this is, hey, this is in fact a negative number. The -2 to the 4th power, we would say, we could rewrite this as 1 over -2 to the 4th. Right? So what we would have is we'd have 1 over, and then we'd actually have 4 copies of this -2 that are appearing in our denominator like this. Okay, so if the negative is in parentheses, if we put it in parentheses, that's good, right? So that's, or I don't want to say good, that means it goes along with the exponent. If it's not in parentheses, then it does not go along with our exponent. Okay, and so then what we would have over here is we should have 1 over 16. Okay, so so let's check this out. Let's bring up a new window here. And so this is from calculus the other day. But let's bring up Desmos, and then let's just double check these. Okay, so if I put these into Desmos, if I write this as -3 to the 4th power, it is verifying, right? So this is in fact -81, right? So that negative did not get raised to the 4th power. If I wanted it to get raised to the 4th power, I could do something like this, where I have it in parentheses, and you should notice that, well, now this is giving me a positive answer. Okay, so when I look at this here, this one's negative, right? The negative didn't get raised to the 4th power, and over here it did. So similarly, if we do the other one, right? So if we have -2 raised to the -4th power, we would get this 0.265, and Desmos will give us the fraction, which is 1 over 16. Okay, so again, it depends on what we want to do. a lot of what we're doing here is we're thinking about this to understand exponent rules, how they work, so that we can model things with exponential functions. If we're just looking for these numerical answers, then Desmos is a good option, right? So if we wanted this -81 or this 1/16, Desmos is a nice option there. Okay. All right, so let's go ahead and let's keep going. Let's do a couple more while we have some time. So let's try 4, 5, 6. Did you all get through 4, 5, 6, or do you need some time to think about those? Time? Okay. Let's take a moment. I'll write them down here. I'll give you a minute to think about these. Hey, Rocky.
Hi.
How are things? So we are looking at some exponent rules right now. So we are in the activity. So chapter 5, we started exponential functions. And so if you want to look at our notes here, we're on page 43 in our book, our activity book, and we just walked through 1, 2, 3, and then we're gonna do 4, 5, 6, and we'll try 7, 8, 9. So everyone else is thinking through these 3 right here. How do we use exponent rules to think about this?
So are we basically combining exponents, like subtracting, multiplying them, and dividing them?
That's
and just
right.
kind
Yeah.
of looking at the properties? Okay.
Yep. So we're like, when do we add exponents? When do we subtract them? When do we, what is it? When do we put them in the denominator? With negative exponents. So
Okay.
I'm gonna mute myself for a minute. Look it. So, are you okay? Yeah. All right. You want to learn some math? Okay. Sorry about that. We have
Cutest.
yeah. She got scared because our dog started barking.
Aw, don't be scared, mamas.
See, don't be scared. You're okay. Oh. You wanna see mommy? Sorry about this. We, adjusting to the new normal around here. Okay. All right. Sorry about that. So where were we? We were thinking about exponent rules and what to do here. So all right. So 27 to the 2/3. Let's think about this as our rules. All right. So when I think about this, I'm viewing this as 27. I'm going to actually break it down as 2 times 1/3. I sort of think about it. I think about it this way, and we can make this 27 to the 1/3, and then put the 2 on the outside like this. Okay, so when I'm thinking about this this way, so this first property right here, 2 times 1/3. Okay, so this 2 times 1/3 right here, that's the same as 2/3. And then we had this property where we actually brought the multiplication down in, and I'm just kind of going the other way, right? So I'm bringing our multiplication out. Now, when I think about this 27 to the 1/3, this is the cube root of 27, which is going to be a number that if I multiply by itself 3 times, I'm going to get 27. And so that's 3, right? So 3 times 3 is 9, times 3 is 27. So this is going to end up just being 3 squared, which is 9. Okay, so when we break that down, sort of that's the thought process that I'm using there. To continue on here, there's a few ways, right? So we could think about this one. I would view this as 5 to the, I would multiply 4 and 2 together. So I would have something like this, right? That's one of our rules. So we'd have 5 to the -8, which we can also write as 1/5 to the 8th. And so if we wanted to think about it, all of these would be equivalent expressions, right? And so depending on what we're looking for, sometimes viewing it this way is a lot simpler than viewing it this way, right? And sometimes viewing 3 squared, that's a lot simpler than viewing it this way over here. Okay, so the purpose of these is these are exercises to get us thinking about exponents and how do we manage them as we move forward. So just to go through this last one here, this should be 1/5 squared plus, and then, right, so I'm going to highlight these so we know what piece is what. So this red right here, right, so I'm going to make this put this in the denominator. And then the next piece right here, so this, we're going to think about this blue piece. So it would be, I would write this as, I'm going to take this square and I'm actually going to square both pieces. So it's going to be 1 squared over 5 squared. Okay, so what this comes out to be is, right, this is 1/25. And then this, right, 1 squared is just 1. And then 5 squared again is 25. And so when I put this all together, I should get 2/25. All right, so how is that for everybody? Can I get a thumbs up, thumbs down? Check in. We get these? So questions on these before I move forward? Good for Carrie. Jody, Rocky, things are good? All right. So I know we had a little extended break there, some excitement. do we get a chance to look at these ones, or do you want a minute to? Good, didn't look at them yet. All right, so let's take a minute and we can think through these. And then we'll take a look at them, right? So I'll give you all a minute, and then we'll go and we'll look at some modeling questions, right? So how do we use these exponent rules to determine exponential models? And we'll look at some data. All right, so we'll take a look at this first one here. So I'm gonna take this step when I deal with this negative exponent, right? So we're talking about putting this in the denominator, and so if I look at this, right, as 1 over 12 over 5, one of the things that we like to say to ourselves is, hey, dividing is the same as multiplying by the reciprocal. So one of the things that is hard for students to think about, a lot of people think about, is this kind of idea of having a fraction inside of a fraction. Right, so I have this fraction where a numerator is 1, and then my denominator is also a fraction. Right, so a particularly challenging situation to deal with. So let's go ahead, let's take this 1 over 12 over 5. We're gonna go off to the side over here, and we'll think about this idea separately. Right, so what if I have this 1 over 12 divided by 5? Okay, so to get out of this, this is what I always think to myself. Dividing is the same as multiplying by the reciprocal. Okay. Have we heard that phrase before, right? Instead of dividing, you can multiply by the reciprocal. So that means, like, hey, instead of dividing by 2, that would be the same as multiplying by a half, right? So they're reciprocal. So instead of dividing by this fraction 12 over 5, I'm going to think about this as this is 1 times, I'm going to multiply, instead of dividing by 12 over 5, I'm going to multiply by the reciprocal of 12 over 5, which is 5 over 12. Okay, so when I look at this, my numerator is 1, my denominator is 12 over 5. This should be the same as, all of this should be the same as 5 over 12. Right, so some work with fractions. Now, when I look at this, this makes a whole lot more sense to me than this over here. Okay, so when we go back, yeah, Rocky, go ahead.
Okay, so anytime you have a negative exponent, would it just always be the reciprocal rather than just putting it over 1?
Correct. Yeah. So that's the way you want to think about it. So the negative in the exponent is like the reciprocal. Yep.
Okay.
So if you wanted to shortcut this, right? So you wouldn't have to do this step right here. Instead, we could think about, right? So we could think about that negative being the reciprocal. And so this would just, if you wanted to, you could just take this straight to 5 over 12 as the reciprocal. Yep. So that's a good way to think about it. So if that makes sense to you as, hey, the negative means reciprocal, that's a great way to think about it. Okay. And so then what we have here is we're going to square each of these, right? So this is 5 squared over 12 squared. And if we want to break that down further, we can use this, make this 25 over 144. Right, so there's, in this one, there's some fraction work that's going on there, and there's some exponent work that we're doing. Okay. All right, so this one here, again, is going to be a lot of the same. Okay, so lots of negatives, right? So we got lots of negative exponents, and then we've got this other negative hanging out here. So as I'm thinking about this, the first thing that I'm going to do is I'm going to think about this as negative 1 over 7. Okay, so I'm going to process this negative exponent. Okay, so I process this negative exponent. I'm going to do the same for my denominator. I'm going to think about processing this negative exponent as well. Okay, so this is going to be negative 1 over 7 divided by 1 over 3 squared. Right, so I'm thinking about it this way on purpose because now, again, we run into one of these situations where we have this fraction inside of a fraction, but if we're saying, hey, I'm dividing by 1 over 3 squared, that's really the same thing as multiplying by the reciprocal, which is 3 squared over 1. Okay, so if you want to think about it like this, right? So instead of you have this fraction inside of a fraction, we can very quickly get out of that. And then this would be 9 over 7, and then we'd have that, still have that negative out there, right? So this should end up simplifying to negative 9 over 7. Okay, so this one is probably one of the more challenging ones that we've seen so far. And then down here in the bottom, we'll do this last one, right? So I'm going to process this numerator. So 5 times 2 is going to give me 10. And then we have 9 to the 8th in the denominator. Now we're dividing, so we're going to subtract them. So we get 9 to the 10 minus 8, which is 9 squared. That ends up being 81. Okay, so we've gone through sort of nine of these examples here. Rocky, you have another question?
Yeah.
Okay, keep going. Keep throwing out there.
Would you wouldn't combine those negative exponents? You would keep them separate?
So what do you mean with on number 8?
Yeah, like you know how you just did how it's like 9 over 10, 9 over 8. I mean 9 to the 10th power, 9 to the 8th power, and then you subtracted them.
Yeah.
Just like on 8, would the denominator and numerator have to be the same in order for that to happen?
That's right. That's exactly right.
Okay.
So over here, what we're thinking of, the reason that I'm subtracting those exponents is because this base, what I'm highlighting in blue here, those are the same.
Okay.
Right. So it's the same base of our exponential term, and then if I come up here, I have a 7, and then this one is a 3, right? So the 7 and the 3, those are our bases. Those are different, so we can't use the same rules. Yeah.
Okay.
That's a great question. Carrie, Mike, Jody, Nick, things are good? Thumbs up, thumbs up. All right. Okay, so this was sort of practice for us, doing some exponent rules, and these are going to be particularly important when we start to think about our exponential functions. Okay, so I'm gonna pull up a new screen here. I'm gonna bring up our notes. And just to remind everybody, right, so there are other videos that I've recorded over this, so you can watch those as well. But when we look at this, right, so we want to now start thinking about functions that have this form right here, f of t equals a times b to the t. Now, our exponent rules are going to be particularly important because our inputs now are going to be these in our exponent. Okay, so we're going to have a times b raised to the tth power. Okay, so you can play along at home here as well. So let's bring up our Desmos graphing calculator again, and I just want to explore. I'm gonna type this equation into Desmos, and we'll go ahead and explore what these different parameters give us. Okay, so I just typed f of t equals a times b to the t, and we can then go through and sort of change these parameters around, this a, and sort of see what's happening, and then we can change this b around and see how it changes our graph. Okay, so what we are claiming here is we don't want certain things to happen. Okay, so we don't want a to be 0. So we're gonna go ahead and we'll sort of explore that. So let's go ahead and make a 0 and see sort of what happens here. Okay. Can we all see where that blue line is? You see that it's right here on the x-axis. Okay, so if a is 0 and I change b around, really kind of nothing happens, right? Right, so we just get this flat line, and this would be a linear function, right? So this is the function, just f of x equals 0 or y equals 0. This would be a straight line. So we're studying exponential functions, so that we want to specifically differentiate them from linear functions, right? So they're new things, they're different. And so this case right here doesn't really give us an exponential function. It doesn't fit into this style that we wanted to. So we're going to exclude that. We don't want a to be 0. And similarly, let's do this one. We don't want b to be equal to 1. Okay, so let's go ahead and make b equal to 1, and then we'll make a something different. So in the case where b is equal to 1, you'll notice that, hey, we get the same type of deal, right? We get this straight line. So again, linear function, not something that we want to include as an exponential function. But if we make it something different, you'll notice that we get this characteristic swoop, right? So we can sort of bend this up and down with A, and we can bend like this for B. So probably in the news, right? So if you've been keeping up with the news, you've probably seen a lot of graphs that look like this, right? So with everything going on right now, we see a lot of information around exponential growth and growth rates and how things are spreading. And lots of the graphs look like this, like an exponential curve. And so this will be the characteristic curve that we're seeing for exponential growth. Now, if b is negative, right, so watch what happens when b is negative, right, our function sort of goes away. It ends up being undefined. And so the reason for that is when we take negative numbers, if we have fractions in here, so if we have fractions like a 1/2 or a 1/4, we saw with our exponent rules that 1/2 would be the same as taking the square root. And so if our base is negative, we don't want to take -2 and raise it to the 1/2 power, because, well, that would cause a problem. We would take the square root of a negative number, which is not what we're doing here, right? We're only working with real numbers. Okay, so we want b to be positive, so we can change this. We want it to be positive, and we just don't want it to be equal to 1. So anything else will be okay. So if b is in this range, if b is between 0 and 1, so one thing that I want to point out to you is if this number right here is less than 1, we see this curve swooping down, right? So see how this curve, it goes down, which means as time goes on, you get less and less of whatever you have, right? So this is called exponential decay. So over time, each time step, we're going to lose sort of some percentage of whatever we had. And then if b is bigger than 1, right, then we get this characteristic that swoops up, right? So this swooping up line, This would be called exponential growth, right? So if you followed along with what we had last week, so on Thursday last week, we talked about R naught in the sort of reproductive rate of the spread of disease, and that goes along with this B right here. So if the reproductive rate is bigger than 1, you get this exponential growth happening, right? And so sometimes we call this the growth rate. And then if it's less than 1, if you get these numbers over here, say 0.8, then that would be exponential decay, which means things are going away, they're dying out. So all this stuff that we're doing right now, we're trying to get this rate to start decreasing, right? We want to get less and less as time goes on, right? So we'll see in our models here that we'll see some growths like this, and we want to actually start to get those things to go down. Okay, so we talked about this, number 1. And so what we can do is we're actually going to use our exponent rules to figure out the equation of an exponential function that goes through 2 points. So what we did before was, when we did linear functions, we took any 2 points on a linear function, and then we were able to find the slope, and we were able to figure out the y-intercept or some other point and find the equation. And so similarly, if we know that we're looking for an exponential function, we can do that same kind of idea. Okay, so we can take 2 points, figure out what B is, what our growth rate is, and then we can determine also what A is, right? So we're going to be looking for these 2 parameters, A and B, that fit our data. Okay, so let's take this information, and what we'll do is we'll think about, excuse me. So we'll think about how I can use exponent rules to figure out the equation, the exponential equation that goes through these 2 points using expressions that look like this. Thanks, Rocky. Okay, so let's go ahead and bring up our Blackboard again. Okay, so the information that we are given is we want to have the exponential function that passes through this point, 2, 126, and the point 3, 756. Right, so the way that you could interpret this data is something like, hey, after 2 days, I had 126 objects, cases, or something like that. And then after 3 days, I had 756 cases. Okay, so we would want to figure out what is that A value, which is going to give us we call those our initial conditions. And then we want to figure out the B value, which is going to be our growth rate. Right, so we're going to have a function that looks something like this. Right, so up at the top, we're going to assume that we have an exponential growth. So we have f of t equals a times b to the t. And our job is to determine what is a and what is b. What is this little capital A and what is little b? Okay, so 2, 126, are you okay? You want to come back and see? Okay, here, but you have to be quiet, okay? So we're going to go through this stuff. Okay, ready? All right, so we have this information, right? So if I have an input of 2, I'm going to have an output of 126. And just remember that, right, whenever we have our input, okay, so our input is going to be this t right here. So our inputs are going to go in for t, right? So this is Daddy's iPad, okay? Yeah. So our inputs are going to go in for t, and then our outputs are going to be out here. They're going to be our f of t. Okay. So we're going to set up 2 equations, and they're going to look something like this. Here, what do you want? You want to use it? You want to use Daddy's phone? Yeah. Can I go see Mama? You want to use Daddy's phone? Okay. What do you want to watch? Can I put Mickey Mouse Clubhouse on? Okay. Okay, ready? And can you go sit over in the chair over there? Here, take this, right? We're going to sit you in the chair. All right, so our inputs are going to be in red here, and our outputs are going to be in blue. Okay, so we want a function that looks like a times b to the t. We don't know what a is, we don't know what b is, so we're going to have right now something that looks like this. Something output equals a times b raised to the input. And so out here, this is going to be my output 126, and then my input here is going to be squared. Okay, we're going to get something very similar over here. We're going to get output equals a times b raised to our input. So we'll have 756 equals a times b cubed. Okay, so I know that since I have this exponential model, I want my points to fit on a curve that looks like this: a times b squared or a times b cubed. And so we can go ahead and try to combine these two equations somehow. And so what we're going to do is I'm going to take this equation right here and I'm going to divide it into the other one. Okay, so in particular, I'm choosing this one to divide by because this exponent is smaller. It doesn't matter, you can do it either way. I like to divide by the one with the smaller exponent just because I can then have positive exponents when this all shakes out. Okay, so we're going to do a division. We're going to take ab cubed and we're going to divide by ab squared. Okay, so we're going to have this. We're going to have an a times b cubed, and we're going to divide by a times b squared, right? So you can think about this as I'm taking this term and I'm dividing by this term right here. And what I know is that this has to be the same as 756 divided by 126. Okay. So we're gonna have this term that looks like this, right? So 756 over 126 is equal to a b cubed over a times b squared. Right, so this so far, we haven't used any exponent rules yet, but this is where they're going to come into play. We're going to have to reduce this expression. Okay, so the first thing that we notice is, hey, I have this a, and those can cancel. And then I have these b's here, and so b cubed over b squared is going to be just b. Okay, so what this gives me is I have this information that the b that I'm looking for, okay, so this b is the same as this b right here, is going to have to be 756 divided by 126. Okay. Okay, so I have this information. B is 756 over 126. And now I need to figure out what a is. So what we'll do is we will go ahead and we can just plug this b back in for one of these equations. Okay, so let's figure out. So if we take our calculator, right, so I'm just going to go ahead and plug it into Desmos. What is 756 divided by 126? Okay, and it turns out that that is 6, right? So this is 6. We'll simplify this. So what we get is 126 is equal to a times 6 squared. And so then if I solve this for a, right, so I get 126 equals A times 36, or A is 126 divided by 36. Okay. Which is 3.5. All right, so let's keep these numbers in mind, right? So our B was 6 and our A is 3.5. Okay. So let's jump back over to Desmos, right? So I'm gonna go ahead and share my other screen. And so what we want is our data that was given to us was 2, 126 was one of our points, and then 3, 756 was another one of our points. So as we're going along here, here's a nice tip, right? So if you want to visualize data quickly in Desmos, they have a nice feature that if you put it into a table, right? So if I put these 2 points into a table, there's a little zoom button. So I can sort of click that zoom and it will bring me into a nice window. And so what we found was that, hey, this f of t is A was 3.5, and I want to multiply by B was 6 raised to the t. Okay. So as we go along here, right, so we have f of t is 3.5 times 6 to the t, right? So this was our A, this was our B that we just figured out. And you can see that this is an exponential model that goes right through these 2 points. Okay. All right, so we had some interruptions there, but did that feel okay to everybody? Do we see how these are coming into play? Thanks, good. Jody, Carrie, Mike, we're good. Rocky, you're good? Yeah, okay. Okay, so given any 2 data points, what we can do is we can figure out, hey, what is the exponential function that goes through those 2 points? Okay, so what I'm going to bring up next is just want to give a quick warning here. So we're going to look at the number of cases. So in the United States, so what I did is I gathered the data. So I called it this COVID-19 data that's over here. And so what we're going to do is we're going to look at the number of cases of COVID-19, so the disease caused by the novel coronavirus. And so we can see sort of what that looks like. So if I look at this data right here, so all of these data points right here, what we did is I gathered the data of the number of coronavirus cases or COVID-19 cases in 2019 or in 2020 so far. So this 0 right here corresponds to March 10th. So on March 10th, we had 754 cases. And then today, 21 days later, so 3 weeks later, so it's March 31st, the latest report said there were 164,000 cases in the US. So if you look at this right here, right, so this shape, right, we get that characteristic exponential growth shape, which looks a lot like this right here, right? So we have this exponential function. We're modeling how these cases are growing, right? So what we could do, we can use an exponential model, right? And we can say, hey, this thing is growing exponentially. What we would like to do is say maybe predict how many cases are there going to be tomorrow, right? So this is 21. So tomorrow would be 22 days after March 10th, which would be April 1st. And so we're going to try to figure out, hey, like, what would we expect? Where would we expect the next data point to be? And so what we could do is we could go through and we could figure out, say, we could try to find an exponential equation that fits this data. Okay, so what we could do is we could use, right, so we could use the process that we just went through to figure out, what is the equation that, say, maybe goes through the first and the last point, or we could, pick some points along the way. So if we picked any two of these points, we could use the same process to find an exponential function. So we're almost out of time here, but what we can do is if you've taken the statistics class, there's a thing called exponential regression. So we could look at this model and we could look at it as an exponential function that fits this data reasonably well. And what we would want to do is we could make a prediction and say something like, hey, how many cases do we expect to see tomorrow, right? So you can see that, the differences here, it's going up by, say, this was 20,000 cases and this was another 20,000 cases. If this exponential growth continued, what we would expect to see is tomorrow there would be 213,000 cases. Fortunately for us, what we're seeing as I'm sort of tracking this data is, notice how this is now below our line, right? So the model, right? So kind of this purple line would be our mathematical model, and this is how we would try and predict what's happening in the future. It's starting to be a little bit below that line here, right? So another more sophisticated model that we use that I alluded to earlier is called a logistic model. So if I restrict my window just to this right here, it still has that swoop up that looks exponential, but it starts to curve down. So if we look at a logistic model, we would look at this and we would predict, like tomorrow, I wouldn't be predicting the 200-something thousand cases. This model would predict that today we have 164,000 cases, and then tomorrow the model is predicting that we'd have 181,000 cases. Okay, so what we can do is we can sort of use this model to predict how many days in the future we are, right? So right now we're here at day 21, and if I want to look 2 days into the future, so this is when we meet on Thursday. So it's Tuesday right now, so 2 days from now would be Thursday. So on Thursday, this model that I've put together through the data is suggesting that we'll have just shy of 200,000 cases on Thursday. So if we want to, we can go ahead and predict, right? So we can make a prediction that we'll see just shy of 200,000 cases on Thursday. And so when we come back, when we all meet on Thursday, we could check in on that and see if this is continuing. So what you want to notice here is that this is good. Okay, so if we're still in the first part of it, right? So if we're still in the exponential phase of this model, okay, things start to get pretty bad pretty quickly, right? So this grows really fast. But if things are starting to level off, that means things are going to start to get better, right? And then so when we're up here on the plateau, right? So this is predicting another 3 weeks from now, we'll be seeing very few new cases, right? So the number of total cases in the US would start to stabilize, and we'll see very few new cases, right? So if this model is true and continues into the future, it's predicting that in about 3 weeks, right? So that would be towards the end of April, we'll start to see very few new cases continue to happen, right? So this is good. And so just some insight into when you're seeing all these predictions in the news, what's the mathematics behind it? And we learned some of that mathematics today, right? So just to recap, and we'll do a little bit more of this on Thursday. So recap, we looked at exponent rules, right? So we looked at our exponent rules. We practiced those a little bit. And then we're starting to think about exponential functions, right? So how would I actually find an exponential function that goes through some values of data? And we're using that to, we use that also to model some of this pandemic that's happening right now. So we can see how these things play out. But this is a very real example of, right, how we're using mathematics, how we're using in the background of all this, right? So we saw exponent rules come into play in order to help us model and predict sort of what's happening out there in the real world, and are things getting better? Are they getting worse? And so this simple model that I put together seems to suggest that things are starting to turn the corner. And so if we keep up our social distancing and our hygiene habits, then things could be pretty good moving forward. I don't want to say good, but they are looking better than they had been, right? So we should start to see fewer new cases, hopefully, in the next coming weeks here. But, all right, so I'm 5 minutes over of our time, but any questions before we go here?
This one, the self-portrait is due this Thursday or next Thursday?
Sunday.
Sunday. Okay, thank
Sunday.
you.
So you have to the end of the week. Yeah. So, yep. So if you want to keep working on that, and then I guess I'll put it in my notes here to if we have questions on Thursday, we can take a look at this, right? So about so. Okay, so yeah, so I'll put that on my agenda. I'll revise this. We'll think about that. I'll field questions about that at the beginning on Thursday.
Okay.
Okay. All right. Well, I'm going to call it here, but email me with any more questions, comments, concerns as we go along. But you should be able to at least tackle a lot of the web work now. So at least the first half of it, and maybe more than that. So. All right. So I'll see you all on Thursday.